Bismillah Rahman Rahim, students. I hope you are fine. Uh, and the fasting month is also going very fast and with your good health. And also, I wish you good health. Last time we were here to discuss the direct interaction and in direct interaction there were several processes. So some processes were explained on the basis of compound nucleus theory, and in some cases we failed to explain the phenomena by compound nuclear theory. In the direct interaction or in all previous topics or current topics, we came across a statement, a concept that is excitation function. So, excitation function actually is a relationship between cross section of a nucleus and energy of the bombarded particle. And this cross section we have to explain for various bombarded particles and target particles. And if you remember, so this one was a graph, and another graph was also explained where excitation function can be seen or can be observed for this type of reaction where one cobalt uh, is used to generate or to produce another cobalt isotope. Now next we have to explain energy of the nuclear reactions. Now, one thing we have to keep in mind that in nuclear reaction, the energy and mass should be conserved. There should be no change in energy and there should be no change in mass during the nuclear reaction. So, law of conservation of energy and law of conservation of mass should be obeyed by all nuclear reactions. Now, let consider these four reactions where thorium is used as target nuclei or nuclear fuel, we can say. In other words, this thorium is bombarded by alpha particle, and definitely in four reactions, the energy of alpha particle must be different from each other. So for this reaction, energy of alpha particle will be different, and for the following reactions, then the energy of alpha particle should change accordingly. In first reaction, what happens? Uranium 235 is produced along with a neutron. In the second reaction, uranium-235 nucleus is produced along with two neutrons, then three neutrons and uranium, four neutrons and uranium. So if you look, what is the difference in these two reactions? Number of neutron produced in the reactions are different, and definitely, as I told you, the production of neutron is dependent on the energy of alpha particles. And then as we discussed, that law of conservation of mass should conserve in nuclear reactions. Therefore, the mass of uranium isotope should change accordingly. So there is one decrease in atomic mass of the uranium nuclei being produced in these reactions, and this is on the basis of number of neutrons produced in each of the reaction. So let's consider the masses of these particles which participate in nuclear reactions. So mass of neutron, you are aware of the digit or the fact that is 1.0090 AMU. Uranium 238 is 232. So sorry, 232 is 232.1095 AMU. 233 is equal to 0.1121 AMU. 234 is this one. Mass of uranium 235 is 235 minus 1172 AMU. For helium is 4.0038, and for thorium is 232.1105 AMU. So let's consider this reaction and represent alpha particle by its exact mass, or the actual particle which we use normally in nuclear reaction for bombarded target nuclei. So thorium is bombarded by helium, and helium is actually regarded as alpha particle. If we ignore electrons in helium nucleus or helium atom, not nucleus, so the remaining portion of helium is now only nucleus, and that nucleus contains two protons and two neutrons. So whenever it is bombarded, on thorium 232. So what happens? Uranium 235 is produced plus one neutron plus some amount of energy, because there will be certain amount of mass which will lost during this nuclear reaction, and that mass is now converted into energy, and we have to calculate the loss mass during this reaction. So amount of energy, normally you are also familiar with calculating the nuclear energy involved during the nuclear reaction. So 931 into mass on reactant sides. So on reactant sides we have thorium 232 and helium, and minus mass, or the difference in mass on left hand side of the arrow and on right hand side of the arrow will give us the idea that how much mass has been lost during this nuclear reaction. So in this case, the mass of uranium plus mass of neutron, the difference between these two species, the masses of these two species, and masses of these two species will give us change in mass during this reaction. So 931, putting the exact values, and these values will give us 931 into minus 0.0119, and the amount of total energy involved in this reaction will come to be minus 11.1 mega electron volt. Now we are now facing the sign which is negative, and is per our knowledge in the field of chemistry, we have to interpret this negative sign, that why the value is negative. So whenever sign of the energy is negative, it means that the reaction is endothermic. And also there are some anomalies in different books. Sometimes they use negative sign for endothermic reactions. Some authors use this negative sign for exothermic reaction. But here we have to make our concept clear, that this negative sign means the reaction is endothermic, and endothermic means we are supposed to provide energy from external source to the reaction in order to initiate it, in order to continue it. So this amount of energy is needed now in one form or another form, and that energy we have to provide is kinetic energy of the particle, of alpha particle. So we are supposed to supply minus 11 mega electron volt kinetic energy to alpha particle in order to initiate this reaction. For other reactions, if you now calculate the amount of energy, whenever you have time, please calculate them. So thorium is bombarded again by alpha particle. Two neutrons have been produced along with a uranium 234 isotope. So the amount of energy involved in this reaction is minus 16.4 mega electron volt. In another reaction where three neutrons have been produced, the amount of energy is minus 23.2 mega electron volts. And in last reaction, the amount of energy being involved or used for the reaction, nuclear reaction, is minus 29.0 mega electron volts. Now compare all four reactions. So in all four reactions, we came across four values. One is minus 11, the other one is minus 16, minus 23, and minus 29 respectively. It means the first reaction carries the first reaction take place at lowest energy, while the last one is at highest energy. It means we have to accelerate alpha particles in order to generate, or in order to produce products of our wish, of our well. If we are interested in production of more neutrons, then we are supposed to increase the amount of energy, the kinetic energy of alpha particle. We are supposed to accelerate alpha particle up to maximum extent. If we are interested in least number of neutrons during this reaction, then we are not supposed to supply or to provide alpha particle with greater energy, because in this case the least energy will produce least number of neutrons, more energy will produce more number number of neutrons. It means that kinetic energy of alpha particle in all these reactions is different, and this different energy, kinetic energy of alpha particle will lead to different products. So this is the idea that how we can control the nuclear reactions, how the products will be obtained, and what measure we have to consider during the nuclear reactions. Thank you.